Okay, so back on question 26, you have your 1,250 kilogram car traveling 6.94 repeating meters per second, and that's its initial, and it comes to a stop. VF is 0. And it comes to a stop in 10 meters. And it wants to know what's the average frictional force. And it's going to be friction that's going to bring it to a stop. Okay, what's the average frictional force that would cause the car to stop? Okay, so we go to work is equal to change in kinetic energy. Work done is F delta D cos theta. And kinetic energy 1/2 mv final squared minus 1/2 mv initial squared. Comes to a stop, VF is 0. We're looking for the force. Divide by, so negative 1/2 v initial squared on the top, divide by delta D cos theta. Cos theta this time, the car is traveling this way, friction is acting opposite. The cos theta is going to be 180. Okay, so you're going to have F is equal to negative 1,250 kilograms. Speed was 6.94 with the 4 repeating meters per second. Over the delta D is 10 meters, and it's the cos of 180, which is negative 1, which is a good thing. It'll get rid of that negative for you. Okay, and so it will tell us that F is equal to, don't forget to square your V, 3,014.0818 newtons. So this is how much force of friction that you need to come to a stop if you're going 25 kilometers per hour. But there's another part to the question that says, if the same car was traveling 50 kilometers per hour when the driver put on the brakes and the car experienced the same average stopping force, how far would it go before coming to a complete stop? So this time we're going to use this force, and we want to find delta D. So going back to F delta D cos theta is equal to 1/2 mvf squared minus 1/2 mvi squared. And again, the final is still 0. This time we're looking for the delta D. So negative 1/2 mvi squared over F delta D. So negative 1/2 m. And this time you're going 50 kilometers per hour. This is 1250. And 50 kilometers per hour is just going to be double the 6.94, so it should be 13.8, I think, repeating. 13.8 meters per second squared. The force is what we found above, 3014.0818 newtons. And the cos is still 180, and that will look after that negative. And this time, you'll get a delta D, if you haven't rounded at all, of 40 meters. And so this goes to your car crash essay, where you probably, doing your research, found things that said doubling the speed will quadruple, multiply by 4 the stopping distance. And then it asked you to do the same thing for 100 kilometers per hour. So cheating, since we already have it rearranged. Delta D is equal to negative 1/2 vi squared over F. I wrote delta D there, and that should have been cos theta, sorry. F cos theta. So negative 1/2 1250 kilograms. And doubling 13.8 should be 2627.7, I think. Repeating meters per second squared. Again, 3014.0818 newtons cos of 180. And this time you should get a crazy 160 meters. So again, doubling the speed changes the stopping distance by a factor of 4. And that's one of the things that's really important when you're driving. Okay, and that you should come across in your car crash essay. You should be talking about in your car crash essay. Okay, so that's the end of all the questions. I now want to go to gravitational potential energy. In class on Friday, we had talked about potential energy as energy being stored in an object. And it means that that energy has the potential to change into something else. And most often, it's kinetic energy that it changes into. A test to see if an object has potential energy is let it go. And if it moves, it did. Okay? And there are several different types. So the first type that we started to talk about on Friday was gravitational potential energy. And so you do work, right? You do work to raise an object. So F delta D cos theta. But when you're lifting an object, the force you're putting on it is just mg. And the height that you lift it, the distance that you lift it is delta D, is really just the height. And if you're lifting it up and it's going up, then the angle is just 0. And so the work done is equal to mg delta h, and we call this the change in gravitational potential energy. So change in then would be mg h final minus mg h initial. But most often we call the initial the 0, whatever height we're lifting it from. So Eg is equal to mgh, and lots of times delta Eg and Eg are the same because the initial is 0. Okay, so here's our two equations that in one class I think we got to on Friday, and in the other class we almost got to on Friday. Okay, in the new sheet that I gave you yesterday, it talks a little bit more about it. So it says gravitational potential energy doesn't really have a lot of use unless it's in reference to something. If we hold an object up and ask how much gravitational potential energy it would have, we have to say with respect to what? The desk, the floor, the ground. We usually call the reference point HI as 0, so that the initial gravitational potential energy is usually 0. So if you lift a 3 kilogram textbook off a desk to 1.2 meters above the desk, how much gravitational potential energy does the book have as a result? So delta Eg is equal to mg delta h, or mg-hf minus mg-hi. And so this is 0. So if you lift it 1.2 meters, that's really your delta h or your h final. So delta Eg is equal to m is 3 kilograms, g is 9.81 meters per second squared, and h is 1.2 meters. So delta Eg is equal to 3 times 1.2 is 3.6 times 9.81, 35.316 joules. Okay? So here are some questions. On page 250, numbers 27 and 29, and on page 250, so I'm skipping 28 on purpose, and on 254, numbers 30 to 34. So this is part of your storm day homework. Okay? But the sheet goes on to talk about another type of potential energy, and it's called elastic potential energy. And elastic potential energy is found in things that stretch. And the most common thing that we'll work with will be springs. But things like spandex clothing have elastic potential energy. You know, some ropes and stuff that will stretch a bit. So it's energy that's stored in an object that's stretched or compressed. So imagine stretching a spring, and I'm holding it out all stretched really far, and then you say, is there a potential energy in that? Well, when I release it, it's going to spring back in. So yes, there was. Or imagine I take the spring and I push it in and push it in and push it in, so it's really compressed. Obviously, as soon as I release it, it's going to spring back out again. Okay? So there's work done to stretch or compress it, and that's what changes the potential energy in the spring. Okay? Now, before we can talk about the elastic potential energy, we have to talk about the force needed to stretch it or compress it. And that's what the next video is going to be, okay?